In today's lecture, we're going to discuss limits of functions. Previously, we've discussed limits of sequences, and now we're going to talk about limits in the context of functions. So our goal ultimately in doing this is to discuss the concept of continuity of a function. So I take it this isn't a completely foreign notion, so you'll recall from calculus. So calculus students are generally taught that a function is continuous at a point if the limit as x approaches that point of f of x exists and is equal to f of c. Okay, so in other words, limit as x approaches c of f of x is equal to f of c. And we'll see that this is basically correct, but there's actually a sort of minor technicality that we'll discuss. But this is the basic idea. Okay, so we're not discussing anything completely new. We just, at the moment, want to clarify this notion of the limit as x approaches c of f of x, what this thing means. Okay, so in this lecture, we'll be just examining this notation, what that means, and then we'll discuss how that's related to continuity in the subsequent lecture. So for now, we're just going to try to be precise about the statement that the limit as x approaches c of f of x is equal to some number L, L being the limit. All right, so we're going to look at the statement that the limit as x goes to c of f of x equals L. So the way you generally explain this to calc students, and this can be your intuition too, I mean, this is the idea of this statement. What this means is that as x gets closer and closer to c, that f of x is getting closer and closer to L. So in other words, we can make this f of x as close to L as we desire just by taking x sufficiently close to c. Okay, so f of x can be made as close to L as we would like, as long as we're willing to take x sufficiently close to c. All right, so that's intuitively what that statement means. And we just want to recall a kind of technical point from the definition of this in calculus, that this statement doesn't say anything about what the function does at the point c. Okay, so in fact, what the function is doing at c is wholly irrelevant in this statement. So the function doesn't even have to be defined at the point c for this statement to make sense. And that the reason for that is, for example, we want to be able to say things like the limit as x approaches 0 of sine of x over x equals 1. Right? Sine of x over x is definitely not defined at 0, but we want to be able to make sense of a statement like that. Okay, so we want to allow for this could make sense even though the function is not even particularly defined at c. And so the function could be doing anything it wants at c, including not being defined at all. So really the only implicit requirement here is that the function be defined arbitrarily close to c. Okay, so we have to be able to make sense of this f of x for x near c, but not necessarily at c. Okay, so to put a little bit more rigor on those 2 points above, so first point, we want to be more precise about the intuitive statement that f of x can be made as close to L as we please as long as x is close enough to c. All right, this is our sort of intuitive idea of what limit as x approaches c of f of x equals L is. That f can be made as close to this L as we'd like as long as x is sufficiently close to c. And as with limits of sequences, it's useful, I think, to frame this as you're trying to convince a skeptic. Okay, so somebody who's skeptical of this claim that you can make f of x as close to L as you please. So a skeptic is going to want to be very rigorous, and they'll say, well, I bet you can't make f of x, within epsilon of L, for whatever their favorite epsilon is. Okay, so it might be 1 over 10, or 1 over 1,000, or 1 over 11 million. So they hand you that epsilon and say, I bet you can't make f of x that close to L. And so your response has to be, well, actually, yes, I can do that as long as I take x, within some particular amount of c. And so that particular amount is often denoted by delta. So what your response has to be is some positive number delta, such that when your x is within delta of that c, okay, so this is your x being close enough to c, so delta is measuring the close enough. I'm close enough to c here, I'm within this, this number delta, then it follows that f of x is indeed close to L in the sense that it's closer than the skeptic's epsilon. Okay, so what we have here, if you just look at this, this statement here, we can kind of put this, see this here is just a quantitative measure of x is close to c, right? And this here is just a quantitative measure of saying that f of x is close to L. So we can kind of read this line here as just saying, as long as, so you have here as long as x is close to c, then f of x is close to L. Okay, which is exactly the same thing as this statement here. As long as x is close to c, f of x is close to L. All right, just sort of a reading the sentence, same sentence in a different way. Okay, so you can see how the intuitive statement is embodied in this more precise logical statement. And so this is essentially going to be the definition of this limit statement here. So we'll be able to turn that into a definition. The second point here, and this is going to also come up in the definition. So remember our second point up here, we said that our f doesn't even have to be defined at c, right? So we really don't care about what's going on at c, but what we do implicitly require is that f be defined close to c. So second point here is that c doesn't need to be in the domain of f, so it doesn't need to be in the domain of f, but it should be a limit point. Okay, so it should be arbitrarily close to points in the domain of f, so it should be a limit point of the domain of f. But it should be a limit point of the domain. All right, so now I'm going to state the formal definition of this limit statement here, and you'll see all of these points encapsulated in that definition. All right, so here's the formal definition. So we have some subset of Rm. Okay, so this definition works for any function from Rm to Rn, essentially. Okay, so in the book you'll see it's from R to R. We've been discussing general Euclidean spaces, so I'll frame it this way, and the definition is really no different in its major components. So we have some subset of Rm on which our function is defined. So the outputs of our function are in Rn, and we have C is a limit point of the domain A. Okay. Then we say that the limit as x approaches c of f of x is L, and this L is some element of Rn, and that's written in the notation that we were discussing above this way. If for every epsilon greater than 0, okay, so this is your skeptic's challenge. Your skeptic is saying, I bet you can't make f of x within epsilon of L. All right, so you're challenged with this epsilon. You have to respond with a delta, such that when your x is in A, okay, so we're talking about the values of our function on x, okay, so x has to be in the domain. So this is just a little technical point. So whenever your x is in A and x is within delta of c, but not necessarily equal to c. Okay, so we're explicitly excluding x equal to c here with this greater than 0 inequality. right? So we're explicitly saying x is not equal to c. So x is close to c but not equal to c. So it's closer to c than delta, then that has to imply that f of x is within epsilon of L. Okay, so basically your skeptic challenges you, says, I bet you can't get f of x within epsilon of L, and you just have to respond by saying, as long as we're this close to c, then in fact we are within epsilon of L. Okay, so that's the entire definition there. And so you see the epsilon and delta that we talked about above, and also that our c is a limit point of A, because we actually have to be able to get x's sort of arbitrarily close to c. All right, so that's the definition. So there's also an alternative way of stating this definition, which is more topological in the sense that it's just phrased in terms of some of the topological concepts that we've been talking about. Actually, it's really just, you shouldn't be put off by this word topological. It's really just reframing these inequalities in terms of open balls. So, for example, so this x in A and 0 less than x minus c less than delta. So this is just saying that, so this thing here, this is just saying that x has to be in the punctured ball of radius delta around c. And this here, right, this just says x is in A, so taking these two conditions together, this just says that x is in A intersect the ball of, punctured ball of radius delta around c, right? And the f of x, so then the f of x minus L less than epsilon, that just says that f of x is in the ball of radius epsilon around L. Okay, so in other words, if you take an x in here, then f of x ends up in here. So one way we can say that is that f, if we look at f of A intersect the punctured ball of radius delta around c, then that's contained in the epsilon ball of radius epsilon, so the ball of radius epsilon around L. So that's a topological way to say that definition. So I'll just write that down carefully for you. Okay, so this is what that looks like. So it's all the same preamble. We have a domain, function defined in that domain, a limit point of the domain, and then the limit statement is equivalent to saying that for every epsilon greater than 0, there is a delta greater than 0, such that the function takes the punctured epsilon ball of radius delta around c intersected with A. Okay, so you're considering all the points in the domain of the function which are within delta of c but not equal to c. That has to be contained within the epsilon ball around L. So all of those function values have to be within epsilon of L. Okay, so really just taking this and this, converting that into a statement about membership in this intersection here, and then combining that with this inequality here to be talking about the ball and the value of the function on the x's from this set. Okay, so that's just an alternative way to say the same thing, just couched in the language of open balls. So you might find it helpful to have a kind of picture of this situation here. So we say, so we have the limit as x approaches c of f of x equal L. So here's your domain A. Okay, so it might be kind of weird. So it has all these like interior points here and some points included on the boundary, but some points not. And then you have all these kind of weird other points here kind of converging on this limit point C. So your domain, I'm just sort of trying to indicate your domain A can be rather general and weird looking, potentially. And so we say that the limit as we approach this point C is equal to L if whenever we take L here and give an epsilon ball around it, that we can always find some delta ball around, some punctured delta ball around C, such that all of the orange stuff that's in A gets mapped over here within this epsilon ball. Okay, so we can always make this delta small enough so that all of that orange stuff stays within this prescribed epsilon ball around L. All right, so that's what the picture looks like associated with this topological version of the definition. Okay, so this is a way to sort of geometrically interpret the definition as given. All right, so let's do a couple of basic examples to make sure we see how this definition works. And I'll take these examples directly from the text so that you have a written down version of these examples already. You don't have to copy them down for yourself. You should just sort of watch me think out loud about how to do these, how to verify these limits using the definition. So here we have f of x is equal to 3x plus 1, and we're going to look at the limit. So we claim that the limit as x approaches 2 of this f of x, of course, that should just be 3 times 2 plus 1, which is 7. Okay, so we have the claim that limit holds, and we will prove it here. So proof. Okay, so your proof should always, basically without exception, start with let epsilon greater than 0 be given. Okay, so you have to allow your skeptic to give an epsilon greater than 0 that you have to beat. So let epsilon greater than 0 be given. Okay, so the next line of the proof, more or less, should be your choice of delta, okay, to respond to this epsilon. So your skeptic wants you to make f of x within this given epsilon of 7, and you have to show that we can do that as long as we take our x within some delta of 2. So we need to produce that delta. And in order to produce that delta, we have to do some scratch work first. Okay, so we need to make, so ultimately our goal is to make f of x minus 7 less than epsilon. So this is our goal. And what does that mean concretely? Well, from our definition, f of x is 3x plus 1. And so we can just do a little arithmetic. So we have 3x minus 6. And that, of course, is equal to 3 times the absolute value of x minus 2. And so what we want is we want to make, right, this thing is just our f of x minus 7. Right? So we want to make this thing less than epsilon. So ultimately, I want to be able to place a less than epsilon over here. And in order to do that, well, all I have control over, so I want to say that that follows from the fact that x minus 2 is greater than 0 and less than delta, right? So all you have control over is this quantity x minus 2 here. You have control over how big that x minus 2 is. So you have control over this x minus 2 thing here. And so in order to make 3 times that less than epsilon, well, so I can specify this x minus 2. So I just sort of have to solve this inequality for the absolute value of x minus 2. So this thing here is just equivalent to absolute value x minus 2 is less than epsilon over 3. So it seems that as long as I take my delta equal to epsilon over 3, I should be able to make this all work out. Okay, so really all this comes down to, as with, and probably you're already sort of seasoned with this from talking about limits of sequences, this is just more or less the same game, just with a slightly different dress on it, because we have delta here instead of n, like we had before. We have the same kind of epsilon, and we're picking delta now instead of n. Okay, so it's the same kind of thing. You're just trying to sort of solve these, try as best you can to solve these inequalities for the thing that you have control over in terms of the epsilon that you're given. Okay, so we just need to take epsilon over 3. That's all we have to remember. We should be able to write the proof based on that. So choose delta equal to epsilon over 3. So then if 0 is less than the distance between x minus 2, which is less than epsilon over 3, it follows that. So note here, just a quick note that the domain of this function is all of R, right? So we're taking here our domain. So maybe I'll just sort of make a parenthetical note that the domain is A equals R. So we don't have to say that X is in A, right? So in the definition, you have to make sure your X is in the domain, but our domain is all of R. So that's not consequential here. So it follows that from this, that the distance between f of x and 7, we're really just repeating our scratch calculation now with our chosen delta in hand. So this is equal to, as we know, the absolute value of 3x plus 1 minus 7, which is the absolute value of 3x minus 6, which is 3 times the absolute value of x minus 2. And that, of course, is less than 3 times epsilon over 3. So this is less than 3 times epsilon over 3, and that equals epsilon. So indeed, the distance between f of x and 7 is less than epsilon. Okay, so that completes the proof in that case. So let's move on to another example. So again, this will be the same as the second example in the book. So you already have it written down. You can just watch the video and not have to worry about copying things down for yourself. Or alternatively, you can, once I write down the example, you can try it for yourself before I work it out and see if you get stuck. So here, we're going to take g of x to be x squared, and we claim that the limit as x approaches 2 of g of x, of course, that should be 4. Okay, so here's the proof. So first of all, beginning of every proof like this, we let epsilon greater than 0 be given. So your skeptical opponent gives you an epsilon that you have to beat. And you want to produce the appropriate delta. Okay, so you need to show that, when x minus 2 is less than some delta and greater than 0, then the distance between g of x and 4 is less than epsilon. Okay, so let's take a look at then that difference, g of x minus 4. And so we ultimately want to make this less than epsilon, and so this is the goal. Okay, well, g of x minus 4, that is x squared minus 4, an absolute value. And of course, being a difference of squares, should be obvious that what we're going to do is factor here. Okay, so we get an absolute value of a product, which is the product of the absolute values, and so we have this factorization. Now, we want to make this less than epsilon, right? And what we have control of is the absolute value of x minus 2. We're sort of trying to solve this inequality for x minus 2, because we want to be able to say, and ultimately what we're trying to identify is our x minus 2. We want to say, if we take that less than some delta, then we can make this less than epsilon. And so the temptation would be to say, okay, absolute value of x minus 2, that should be less than epsilon over the absolute value of x plus 2. Except the problem is this is not a number. Right? So this is not a number because x is a variable. Right? So it's not a number because it involves x. So this is not a suitable delta. Okay, so that's not going to work for delta, so we have to do something else. All right, so we don't get off that easy in this case. This is not as straightforward as the last one. All right, so in the last one we did a little bit of algebra, and we just got a number times our relevant quantity here, and we could just move that number to the other side, solve the inequality. But this time we don't have a number, we have this this variable expression. So we sort of have to replace this absolute value of x plus 2 with a number. And what we're going to do is, so what we want to do is take this absolute value of x minus 2 times absolute value of x plus 2. I want to sort of say that this is less than the absolute value of x minus 2 times some number, I don't know, let's say a, right? And then what we'll do is we'll try to make that less than epsilon. Okay, so if we can replace this thing here by a number, in other words, what we want to say, so we would want to say that the absolute value of x plus 2 is less than some number a. And so if we can do that, then we can put an inequality in here, and then once we have a number there, we can make that less than epsilon just by making absolute value of x minus 2 less than epsilon over a. So what we need is to control the distance between, so the absolute value of x plus 2, which is really the distance between x and negative 2. All right, so to sort of summarize this idea here is what we need to do is we need to control the absolute value of x plus 2. So we want to say that the absolute value of x plus 2 is less than a. And so our interpretation is the absolute value of x plus 2, that's just the distance between x and negative 2. Okay, and so roughly the intuition goes like this. So here we have, so what we can do is we can take our x as close to 2, right? We're allowed to arbitrarily control the distance between x and 2. We can take x as close to 2 as we would like. So if we envision our number line, we have 2 here. Negative 2 is all the way over here. And we have 0 in the middle. And so what we can do is we can take our x, as close to 2 as we would like. And so say, if we constrain our x so that it's within a distance of 1 of 2, right? So if we take our x such that it lies in the interval from 1 to 3, then definitely that's going to put a bound on the distance between x and negative 2. Right? So the furthest that x could be from negative 2, if x resides in this interval here, is a distance of, let's see, looks like 5. So basically what we note here is that if the distance between x and 2 is less than 1, then the distance between x and negative 2, which is to say the absolute value of x plus 2, is less than 5. So this is visually apparent from the picture, and we can substantiate this using the triangle inequality. So the distance from x to negative 2, what I can do is I can use the triangle inequality to say that this is less than or equal to the distance from x to 2. And so we're measuring the distance from x to negative 2. Make 2 the middleman. Okay, so this is less than or equal to the distance from x to 2 plus the distance from 2 to negative 2. Okay, and this is so this is 4 plus the distance from x to 2, and we're assuming that the distance from x to 2 is less than 1. So this is less than 5. Okay, so provided that x is within a distance of 1 of 2, that puts this x plus 2 under control. Its length is, or its the distance from x to negative 2 is less than 5. And so if we go back up to here, we see that we can write this is less than 5 times the absolute value of x minus 2, and this will be provided the distance between x and 2 is less than 1. And then ultimately we want to make this less than epsilon, so we also want to ensure that the absolute value of x minus 2 is less than epsilon over 5. Okay, so all told, we have two conditions on this delta here, right? So basically we want our delta to be either, we want delta to be smaller than 1 and smaller than epsilon over 5. Right? So basically we want delta to be the minimum of 1 and epsilon over 5. So we need the absolute value of x minus 2 to be less than 1 in order to get this inequality that we needed here, and we need it to be less than epsilon over 5 in order to get the second inequality. Okay, so we need both of these inequalities, and we'll just put them together in into one by making delta to be the smaller of whatever of these two. Okay, so that is all of the intuition for our proof, and so we will go ahead and write it, and just remember that we want our delta to be the minimum of epsilon over 5 and 1. Okay, so I erased everything except the delta, which I can erase after I write this next line. So we choose delta to be the minimum of epsilon over 5 and 1. Okay, so now I can erase this. Okay, so before we actually look at, so ultimately what we want to show is that the distance between x squared and 4, right, is less than epsilon from this. And we know we're going to get absolute value of x minus 2, absolute value of x plus 2. And what we need to say is that absolute value of x plus 2, we need to say that's less than 5. Right, and then it'll be immediate from that. All right, now that this absolute value of x minus 2 is going to be less than delta, which is less than or equal to epsilon over 5, we'll have immediately that this is less than 5 times epsilon over 5. That will give us epsilon. But so the point is, first we need this absolute value of x plus 2 less than 5. So we need that inequality before we go and do this whole line here. So I'm going to establish that preliminary inequality first. So what we'll say is, so if 0 is less than absolute value x minus 2 is less than delta, then in particular, the absolute value of x minus 2 is less than 1, since delta is less than or equal to 1. As a consequence, the absolute value of x plus 2 is less than or equal to absolute value of x minus 2, or maybe I should let's make this cleaner. Okay, so absolute value of x plus 2. Right, so I'll just maybe be clear about this triangle inequality. So really what we're doing is just a plus minus trick. So we have x minus 2 and then plus 2 plus 2. So that's less than or equal to absolute value of x minus 2 plus absolute value of the 2 plus 2, or 4. Okay, so that's just 4 4 plus the absolute value of x minus 2, and we know the absolute value of x minus 2 is less than 1. So this is less than 1 plus 4, which equals 5. So then thus absolute value of x minus 2 between 0 and delta implies, and here's where we're going in for the kill. So it implies the distance between g of x and 4, g of x being x squared minus 4. This is absolute value of x minus 2 times x plus 2 in absolute value. Now we know, right, we have the x plus 2 inequality at our disposal now, so we don't have to interrupt this computation here. So this is just less than 5 times absolute value of x minus 2. We know the absolute value of x minus 2 is less than delta, so this is less than 5 times delta. And delta is less than or equal to epsilon over 5 by our choice. So this is less than or equal to 5 times epsilon over 5, and that is equal to epsilon indeed. Okay, so that completes the proof there. All right, so you see the process is very much similar to what you did when we were talking about limits of sequences. It's once you give the epsilon, you're trying to make your g of x minus L less than epsilon, and you have to do some scratch work, do some algebra, and try to work that out. See how many, take into account whatever conditions you need on x, in this case on x minus 2 to get to the conclusion. In this case, we needed 2 conditions, and so that involved taking our delta to be a minimum. So now that we've established a definition and looked at a couple examples, it's natural to consider general properties of this definition of limit, functional limit. And so, some standard ones from calculus that you would expect. For example, we could look at the limit of a sum of functions, assuming the functions are defined on some common domain and C is a limit point of that domain, then we would want to have this be equal to the sum of the limits. And we can make an argument for this directly based on our definition. And, we'd have other properties too. Like, for example, we'd have the product of 2 functions and their limit being the product of the limits. But it would involve a good bit of work to do all of these sort of standard limit properties. And we already did the corresponding properties for limits of sequences. So the sort of clever route that we're going to pursue here is to relate our definition of functional limit to limit of sequence. So we could argue for these properties directly from the definition. But a more time-efficient way of going about this, but it's more efficient to use the work we did for sequences in the algebraic limit theorem. So what we're going to do is, so the sort of new goal here is, so to relate limit as x goes to c of f of x equals L to statement about limit of sequences. To a statement about limits of sequences. And if you might want to pause for a second and see if you can, come up with the natural, so we're going to state a theorem that says that this concept of limit here is equivalent to some statement about limits of sequences, and you might want to just think about what the natural thing is. So it's fairly straightforward. The statement of the theorem is fairly straightforward based on the fact that C, so the sort of hint here is that C is a limit point of the domain. Okay, so that's sort of related to how you get the sequences. All right, so here's the theorem. So this is the sequential criterion for functional limits. It's just an equivalent way of talking about the limit of a function as you approach a particular point. So we have some domain in Rm, a function from that domain to Rn, and a limit point of the domain. Then the following statements are equivalent. The limit as x approaches c of f of x equals L, as we've been discussing. And then this other statement here. So where this statement comes from, basically this first thing, this limit says that as x gets close to c, right, whenever x is close to c, then f of x is closer to, getting closer and closer to L. So as x gets closer and closer to c, f of x gets closer and closer to L. Well, this second thing is just sort of specifying a particular way in which x gets close to c. So the way that's formulated is in terms of a sequence. So you take a particular way in which you get close to c. So you have a sequence xn of elements in A, but not equal to C. Okay, so C may or may not be in A. So we if C is in A, we want to make sure the xn's are not equal to that C. So we have this sequence in A, but the sequence does never includes C, and but we have that sequence approaching C. Okay, so we're taking a bunch of x's which are getting closer and closer to C. And if that's happening, then the f of x's, the corresponding f of x's, are getting closer and closer to L. Okay, so sort of saying it that way sort of makes it obvious, right? One is just one way, so this thing, when you unpack the definition, it just says as x gets close to c, then f of x gets close to L. This second thing is exactly saying the same thing. It's just saying, no matter how you get close to c, your f of x's are getting close to L. Really just two ways of kind of saying the same thing, but we want to verify that, based on our definitions, that these two things really are equivalent. Okay, so when you sort of zoom out and say them intuitively in the English language, they're sort of obviously equivalent, and we're just going to verify that they're equivalent based on the definitions that we've given. Okay, so one way is fairly easy here. So let's say see that 1 implies 2. Okay, so what we're doing here is we're supposing, so suppose that limit as x goes to c of f of x equals L, and let xn taken from A but never equal to C be such that xn goes to C. And so what we have to do is say that the f of xn's go to L. So we're talking in the language of sequences here, so this is the convergence of a sequence. So to say that convergence, that sequence is converging, we're in epsilon n language, right? So we let epsilon greater than 0 be given. Well, what we need to do is say that the f of xn is within epsilon of L, right? But what we know is that we have this limit, right, is equal to L. So what we know is that f of x minus L, we can make that less than epsilon just by taking, right, so as long as we take our x, there's going to be some delta, so that when x minus c is less than delta, that f of x minus L less than epsilon will follow. And so what we need to do is ensure that these xn's are within delta of c. So basically here, in order to make f of xn minus L, less than epsilon, what we need is for the xn minus c, we need that to be less than delta. But of course, we can make the xn within delta of c because xn is converging to c, right? So there's going to be some capital N such that when n is bigger than that capital N, the xn's are within this delta of c. Okay, so for this epsilon greater than 0 given, we have to hit this target here. Well, this target, right, because of our limit statement here, we know that as long as we can hit this target, as long as the xn's can get within that delta of c. Right? So for this epsilon, there's a delta response because we are supposing this. And then with that delta, well, we also have the convergence of this sequence xn to c, and so we can get within delta of c. Right? There's an appropriate n response because of the convergence here. So the n response to this delta will cause the xn's, right, their f values to be within epsilon of L. Okay, so that's the sort of chain. To this epsilon, we have a delta response by this, and for this delta, we have an n response to that delta because of the convergence of that sequence there. Okay, so that's the relatively straightforward structure of this proof here. So let epsilon greater than 0 be given. So then there is a delta greater than 0 such that x in A and 0 less than x minus c, an absolute value less than delta, implies that the distance between f of x and L is less than epsilon. Okay, so then all we have to do is hit this delta target with our, so we just want to make our xn's within that delta of c. Okay, so since xn converges to c, there is an n such that little n bigger than or equal to big N implies that the distance between xn and c is less than delta. So therefore, just putting this all together, if little n is bigger than or equal to n, then 0 is less than absolute value xn minus c is less than delta, since xn is never equal to c. So f of xn minus L less than epsilon follows. Okay, so thus we have an n response to the given epsilon. And so that completes the first part of the proof. So the second part is to prove that 2 implies 1. Okay, so for 2 implies 1, we suppose that whenever we have a sequence of things in A but are never C, and those things converging to C, suppose that implies that f of x sub n converges to L. So what we need to show is that the limit as x approaches C of f of x equals L. Okay, so we want to show that the limit as x approaches C of f of x equals L. So that is, we need to let epsilon be greater than 0, and we need to show that there's an appropriate delta response. So it's not very obvious where that delta should come from based on the information given, right? We just have a bunch of sequences. How we're going to cook up that delta is not really clear. So the way forward is to consider a proof by contradiction. Okay, so to actually get somewhere here, we're going to do a proof by contradiction. So suppose, for the sake of contradiction, that the limit as x approaches C of f of x is not equal to L. Okay, so what does this mean? So this means that the skeptic can win, right? So this means the skeptic can produce an epsilon that can't be beaten. So thus, there is an epsilon greater than 0 such that no matter how hard we try, right, no matter what delta we try, we're always going to fail to show that f of x is within epsilon of L. So such that for any delta greater than 0, well, what happens is that we're not going to be able to pass our challenge, right? So f of x minus L is going to be greater than or equal to epsilon for some x in A, right? For some x in A, which is within delta of C. So there's something close to C in A which fails this challenge. So such that for any delta greater than 0, there is an x in A such that x minus C, x minus C, I always forget the 0, 0 less than absolute value of x minus C less than delta, but f of x minus L is not less than epsilon. Okay, so that's the setup. And so what we're going to do is essentially produce a sequence, right? So we're assuming that we have these this limit implication for any sequence, and we're going to be able to cook up a sequence here because now for any choice of epsilon, right, we're going to have produced for us an x, right? So for any epsilon, there is an epsilon such that for any delta, so any delta we choose here is going to produce an x that fails the challenge. Okay, and so what we can do is, for this given epsilon, we can take our delta to be, say, 1 over n, right? So just a sequence of deltas 1 over n, we'll get a corresponding sequence of xn's that are failing this challenge, but then that's going to produce a contradiction. Okay, so considering delta equals 1 over n, we obtain a sequence of xn in A such that xn is within 1 over n of C, but f of xn minus L is greater than or equal to epsilon. Okay, so clearly xn is converging to C. So clearly this sequence of xn is converging to C, right? And also xn, by construction, they're in A, right? They're in A, and since we have greater than 0 here, they're not equal to C. So this is in A, but they're never equal to C. So thus, the f of xn's must be converging to L by assumption. Okay, but you see this is an obvious problem because the fact that f of xn goes to L means we have to be able to make it arbitrarily close to L. Right, so we have to be able to make it, say, within epsilon of L, but these f of xn's are never within this epsilon of L. So since f of xn approaches L, using the epsilon from above, epsilon greater than 0 from above, there has to be an n, big N, such that little n bigger than or equal to big N implies that f of xn is within epsilon of L. But this contradicts the fact that f of xn is explicitly further away than epsilon from L. All right, and so that completes the proof. So an immediate corollary of this is the algebraic limit theorem for functional limits. So in this case, we have two functions defined on the same domain in Rm, and we have a limit point C of A, and we suppose that the limits of these two functions both exist. Then the limit of a constant times a function is just the constant times the limit. Limit of a sum is the sum of the limits. Limit of a product is the product of the limits. And the limit of a quotient is the quotient of the limits, provided that the quotient on the right-hand side makes sense, so that that limit of g is not equal to 0. And so the proof of this is pretty much immediate. So this is an easy consequence, of the algebraic limit theorem for sequences and the sequential characterization above. Okay, so I'll leave it to you as an exercise to see that this really is an easy consequence of these two facts. So another corollary, which is nice, is a simple way of seeing that a limit does not exist, so a functional limit does not exist. So this is a divergence criterion for functional limits. So the criterion for divergence is the following, right? So typical setup, we have a function defined in a domain, we have a limit point of the domain, and what we'll have is suppose we have two sequences in this domain, but not equal to C, but the sequences converge to C, and the function values on these two sequences converge to different limits. So if those sequences of function values converge to different limits, then the limit as x approaches c of the function does not exist. And this is just a straightforward corollary. So the proof is just, this is immediate from the sequential characterization. Because if the limit were to exist, then any sequences like this converging to C would have to all have the same limit, right? They all have the limit L, right? Whatever the limit is here, that would have to be the limits of these function value sequences from the sequential characterization. So if you have two different function limits along two different sequences, then your limit can't exist. So a couple of examples. So define the function f of x to be 1 if x is a rational number, and 0 if x is not a rational number. So this function is called chi sub q. This is the indicator function of the rationals. Indicator function of q. So with this, this function, so the limit as x approaches c for any c of f of x does not exist. For any c. And why is that? Well, for any c, in the real numbers, we can construct a sequence of rationals which converge to C and a sequence of irrationals which converge to C. So this is easy to do based on just general theorems we've talked about, right? So between any two real numbers, there's always a rational number, and between any two real numbers, there's always an irrational. So you can use that easily to construct sequences of such rationals and irrationals converging to the C. So we can find a sequence xn of rationals, so rationals that are not the number C, and yn, which is in the complement of the rationals, so the irrationals, minus this C, such that xn and yn both go to C. But the f of x's, so f of xn is equal to 1 for all n by definition, and f of yn is equal to 0 for all n by definition. So the f of xn, that converges to 1 since it's a constant sequence, and f of yn converges to 0. And 1 doesn't equal 0, so 1 is not equal to 0. So that implies that by this corollary that we were just discussing, that the limit as x approaches c of f of x does not exist. Okay. So that's one example of showing that a limit doesn't exist using this sequential characterization. So this is much easier than having to go through the definition. Kind of annoying to use the definition to show that these limits don't exist. And another one, and this will be our last example for class for this lecture, is the example of sine of 1 over x. So sine of 1 over x. So you might remember this function as an example from calculus. So as x goes to 0, 1 over x goes to infinity. So for example, in the window from 0 to 1 here, you have 1 over x, right? So you've applied 1 over x to the interval from 0 to 1. That takes you to the interval from 1 to infinity. And in the interval from 1 to infinity, sine is doing an infinite amount of oscillating, and that oscillating is nice and even in the interval from 1 to infinity, but you're taking all of that oscillating and you're crunching it into the interval between 0 and 1. So you get this really wild thing where things aren't so bad out here. It actually is getting stretched out, but then it's getting severely compressed in here, and you just get this total mess, right? And so you get some function that looks like that. And so we can use this corollary to show. So the claim is that the limit as x approaches 0 of sine of 1 over x does not exist. So the basic idea for doing that would be to get the peaks here, so all these 1s as you come in to the origin, and then all of the negative ones. So what we need is so sine of 1 over x equal to 1, and sine of 1 over x equal to negative 1. So sine is equal to 1. That's going to happen when 1 over x is, right, so when you have pi over 2 and then plus like 2 pi n, right, so any multiple of 2 pi, and then with the negative 1, that's going to be 3 pi over 2 plus 2 pi n. So just inverting that will give you sequences of x. So what we can do is consider, so let's consider, so you take xn and make that 1 over pi over 2 plus 2 pi n, and yn to be 1 over 3 pi over 2 plus 2 pi n. Then, of course, sort of just by construction, we have the f of xn that goes to 1, the f of yn that goes to negative 1, but of course the xn and yn go to 0. And so it's easy to establish that they go to 0. So I guess this would just be an easy to check. Okay, so that establishes the claim. So thus, and notice that xn and yn, they're never actually equal to 0. So these are sequences that are approaching 0 but not equal to 0. So thus, the limit as x approaches 0 of sine of 1 over x does not exist, as claimed. All right, so that's it for the notion of limits of functions, and next time we'll define continuity and we'll see how this is related to the notion of continuity of a function.